And an hour later, I said, oh crap.
Yeah. Thank you, Riley, for the lab. The data for this in the video that I saw already posted on Blackboard.
Right.
Do you give data in video while
Yes.
conducting that?
Yeah.
That's
It's more than just entertainment.
okay.
I don't remember the statistics. When everything went into lockdown, there was a survey of physics instructors about how they dealt with the labs. And it's like a third of them did what I did the video and students pulled the data from it. A third of them did some sort of online simulation, and a third was more of a here's the data.
Interesting that they would just do here's the data.
Well, it was sort of a sudden thing.
Yeah. What a wild time. It feels like that was like 8 years ago instead of just like a couple.
Yeah, time lost some meaning there. Alright, so we're doing rotational motion. Okay. Any questions?
This is all the way back to work, but when we were doing the snowboarding problem,
Yep.
there could have been some instances where our displacement was going this way, but our weight was going downward, right?
The weight is always going downward. Yeah.
Yeah, but our displacement would be going to the right.
Yep.
So that would mean they're perpendicular components, so the work would equal 0 at that point, right?
Yeah, but the nice thing about energy is once you establish that only conservative work is being done, then you only care about the beginning and the end. You don't care about anything that happens in the middle.
But on that stop, he would still have a 0 work because the force is perpendicular to the displacement, right?
So he starts, so at the very beginning, there has to be some conceit that he does start sliding down at some point. So if he's just at the precipice, that's what I'll find you want to split the hair. I guess you can make an argument that the initial work was close enough to 0 to count. But still, work is a conservative force. All I care about is the beginning and end. I don't care about what happens in the middle.
All right.
Ultimately, it's found by, we did the derivation. I'm going to retract what I started there.
But the equation for work conservative, is it negative potential energy or positive changing?
Negative change in potential energy.
So the equation would be potential energy initial minus potential energy final?
Yes, once you distribute the negative sign.
Okay.
I'm seeing happy faces here.
Yay.
That's right.
Can you do me a favor? And I think I don't have a good idea of like what I'm doing with my hand when we do the thing. Like, you know, because like yesterday you were like, it's this way. And I was like, I don't know what that
Okay,
means.
first off, right hand. Okay, so when you're doing, and then you wave, jazz hands,
This is
twinkle fingers.
just.
Is that a thing?
Yes.
And all of that connects to physics. So when you're doing all of it has been under the basis of cross products.
Yeah.
And it's just that when you've got two vectors for which you're crossing the products, one way of looking at it is the way that I've been trying to go about it is if I'm doing A cross B, put your hand in the direction of the first one, which would be down at an angle. So basically 360 degrees, I can turn my hand in theory.
Yeah.
But you want it so your fingers bend towards the second one, the shortest path. So my hand's down like that.
Yeah,
So since it's a two-dimensional problem, my hand's either going to be like this or like that.
okay,
Well, B is closer if I go this way.
yeah,
Thumb points in the direction of the product.
okay. How do you know, this is so stupid, I'm sorry. How do you know when it's like this or like this?
It's by which way when your fingers bend, they want to bend the fastest
Oh.
way to get to the second vector.
Okay, I get it.
So I want to avoid the argument of, yeah, I can bend that way and go all the way around, but yeah, the fastest way is this way.
Okay.
How do we know from which vector we should start? Because if we started from B,
That's right. Commutative property does not hold, the order does matter. So in the case of this, I started with, if we're doing A cross B, if we did B cross A, well, that would be a vector pointing
Okay.
that way. Torque is R cross F,
okay,
not F cross R. That formula is set.
okay.
Okay, that was really what I think I was trying to ask, so thank you.
Okay. Yeah, whichever, if I said, do the cross product of these, there, without any more information,
It could be.
there'd be two answers. And that's a situation where potentially you're going to go, if I did that on a test, if I didn't write what are the answers, plural, or I need only one, somehow give some indication that there's two answers, that might be a time to come up and say, did you mean for there to be more than one answer? At which point I'd go, yes, or, oh, oops. Another way of looking at it, no, I think that's just going to make it more confusing, so I'm going to draw that too. If you're dealing specifically with torque, the question is, so when we were doing the beam problem yesterday, and we had a force up here, force up here, force down here, if it's in static equilibrium, you pick any point. And it's a question of, if I pick this as my axis of rotation, then imagine my beam here, and I basically got a pin in it, so that's a spin. It's going to spin about that point. This force right here is going to try to cause it to spin clockwise. So this has a, if we go with the traditional I hat, J hat, K hat, this would have a negative K hat torque. This one is going to try to spin it counterclockwise, out of the board. This is going to try to spin it clockwise, into the board.
Shouldn't the K hat be an X? Because we said it was towards the board?
I cross J is K, so I cross J. Okay.
But that's when we would pick a point that is essentially where one of those tension forces is acting, so that we can
So-
eliminate.
Yeah, so if we pick that as the point, this has no torque.
Yeah.
This would have torque into the board. This would have torque out of the board.
Okay.
So negative K hat torque, positive K hat torque. No other questions?
Wait, one last question, sorry. So yesterday we said like if we put the coordinate axis in like a alphabetical order, like IJ K, and then we put IJ, we will, and then you just multiply like IJ equals K. If we mix them up saying JIK, that wouldn't work, right?
Right, so if you're doing J, I, K, you have to go in that direction. Given the way we wrote it on the board, so that would be negative.
Okay.
J cross I is negative K.
All right.
Or J cross I, negative K.
Okay.
And my right-handed coordinate system video is my most popular video. It's like 11,000 views. There was a Intel ad where they had the two nerdy installers, and one of them said, I put your post, it's got 7 likes. That's pretty much, I know where it's coming from.
You said yesterday that if we look at the
Rube Goldberg.
test, that it would cover pretty much all of the material.
Yes.
Is it going to cover more material than what is going to be on the test? Or just
Not necessarily. It covers more material than we have covered up to now.
Okay, but we might cover all that before.
Yes.
Okay.
Are we going to get to like fluid mechanics or something like that?
Are we going to do fluid mechanics? That's not how much time we got. Once we get through vibrations, then it's a question of how much time do I have left to do a little bit of thermo and a little bit of fluids.
And that'll be part of the test too, right?
The vibrations probably will be.
Okay.
Fluids, I don't know. Thermo, I don't know. All right, other questions? Did you bring enough for everybody?
She did. I was just break them into really small pieces.
Okay, that's all that matters. Let's do the ladder problem. Ladder. Let's make it 10 kilograms. Person. Mass of the person. We'll make it 70 kilograms. I'm gonna make this angle here. Make it target small. Let's make it 57 degrees. Here we'll have a use of S is 0.3, and here use of S equals use of K equals 0. So frictionless wall, we have friction down at the base. The question is, how far up the ladder can this person stand before the ladder slips? So I'm looking for a distance from here to here, which I will cleverly label X. How far up the ladder can he go before the ladder slips? We'll start this out the same way that we started out every problem for the past month. With?
Force diagram.
Yeah. So I have ladder, person, wall, ground. That's it. And this is a ladder, this is not a ramp.
Friction on the bottom to the ground is to the right.
On the ground? Is that what you said?
On the ladder.
On the ladder, so right there, is that what you're saying?
Yeah.
Okay, so friction. Because if the ladder slips, that bottom is going to move to the left, and therefore friction says, not on my watch. As best as I can. One down. If we're doing a full diagram, what the heck? Ultimately, I only care really about the forces on the ladder, but
There's weight acting on the ladder and the person.
weight of ladder. Oh, I do need to give length of ladder. Make it a 15-meter long ladder. And then weight of person.
there a normal force between the ladder and the person?
Yes. Which way is the normal force acting on the person?
Perpendicular to the ladder.
Oh yeah. Well,
It's a ladder, not a ramp.
So it has to go that way
When
because
you stand on a ladder, you stand on the rung. So
Okay.
your feet are like this. So the normal force is up. That's one of the reasons why I said it's a ladder, not a ramp. If we made it a ramp, then that'd be a slightly more difficult problem. So YP and YB.
is there friction on the ladder itself?
What friction between?
The person in the ladder?
We will assume not. We assume that he has incredible balance.
Okay.
Would there be normal force between the points that the ladder is touching the ground and touching the wall?
I hope so. So I got Y sub, I'm gonna call this 1. Y sub 1.
Also normal force on the wall and the ladder?
Y sub 2. Y sub 2. No tension, no other. We've got the 2 gravitational force pairs. We've got 3 points of contact, so we have 3 normal force pairs. Friction only in one spot. So yep, we're done. What's next?
Equations of motion.
Equations?
You're gonna go straight to the equations.
Oh,
Okay.
No.
coordinate axes.
Direction of acceleration.
To the right?
So what's the problem? In terms, what are we trying to find?
How up the person will go around.
Before what?
When the
The
ladder
ladder
falls.
slips.
So we're having this issue of at what point the ladder is going to slip. Recognize how far up the ladder it goes before it slips. We're looking at that point, that last point where it will not slip. In other words, it's in static equilibrium until it slips, so we're looking for that breaking point. So we want, so it's in static equilibrium. That's what I'm heading towards. So the acceleration therefore is
0.
so when we set up our coordinate axes, I recommend something that's going to require us to break up as few vectors as possible.
To the right and up.
That works.
Why is it on static equilibrium again?
Pardon?
Why is it on static equilibrium again?
Because we're looking for that last point before it slips. So it hasn't slipped yet, so it's just sitting there.
Okay.
I'm assuming that the ground is still and
But there's
yeah, it's not slipping. Relative to the ground, it's not moving.
And we didn't say anything about the person because and the ladder because we're not looking for that, right? We didn't indicate an acceleration between the ladder and the person.
Right, the person's just standing there
Okay.
and moving very slowly from one rung to the other. We will assume that the normal force he exerts is equal to his weight. Now, in reality, as you step up, your center of mass is moving up slightly, which means the normal force will be greater than the weight, briefly. But we assume he's moving slowly enough that they are close enough to the same. Or if you prefer, through magic, the person is placed at that breaking point. Or less magical, the person came into existence, despite the odds, standing on a ladder just before it slipped. All right, coordinate axes, decomposition, none. That was easy. All right, equations of motion. I care about the ladder. So I am going to simplify one aspect here. If I'm making the concession that these two are close enough to equal the count, then this just equals the weight of the person. So now I can look at just the ladder. How many equations of motion will we have?
2.
We'll actually have 3, but we'll start out with 2.
Oh, wait, because of torque.
Yeah.
Wait, where would we use torque though?
Pardon?
Where would we use torque?
Well, why don't we come up with 2 and then figure out how we're solving for x, so x will not come in and just horizontal and vertical.
Friction minus y2
So friction minus y2
equals ml0.
All right. Next.
y1 minus wl minus yb equals 0.
So as we're solving for x, x does not show up in here as was just mentioned, and as Ritika did not mention it. So we do need to have torque in there in order to account for, in order to get x into it. But in order to do torque, we need an axis of rotation, but this object's not rotating. So where should we pick our axis of rotation?
In the middle.
Where the weight is acting? Weight of the ladder is acting?
Yeah.
Okay. If we do that, how many torques have we eliminated?
No.
Oh, none.
Put it on the end.
Sorry, what? I heard none?
Yeah.
What would the torque from the weight of the ladder be?
Is it from the...
Talking too softly for me to understand. Torque happens when the force is not acting through your axis of rotation. So in this particular case, if we choose this